Hi everybody. In this video, we are going to be talking about 18.3.1, which is Introduction to Natural and Common Logs. And we're first just going to start about just kind of giving you a general overview of what in the world they are and how do we find them on our calculator. And then we'll move into learning about how to graph them too. All right, so the first link is going to be numbers. So almost any number can be the base in both exponential and logarithmic functions. However, there are two bases that are used so frequently that mathematicians have special names for the logarithms. And there are also special buttons on our scientific and graphing calculators, which is what this next sentence was saying. So these are called the common and natural logarithms. So, and we're getting ready to go talk about it, but just so you have like a little brief overview here, the common log is going to be base 10. And it's the one on your calculator that just says log. And then the natural log is going to be base E. So Euler's number. And the button on your calculator says ln for natural log. That's just kind of your little brief overview right there. So common logarithms, and again, we're talking about common now, not natural. So common logarithms, traditionally base 10 logarithms were used most often because our number system has a base 10. So that's what we're gonna fill in there, has a base of 10. Logarithms with base 10 are called common logarithms. And log base 10 of x is abbreviated as just log of x. So I talked about that in a previous example, I don't even know, like a video or two ago, and we were doing an example with log base 10, and I said, you know, we don't even need to write the 10 on there because a log, like if you just write log of x, that's assumed that it's base 10. So just like we would take the square root of 64, the square root, we just assume that it's a square root, so we don't write in the index of 2 for a square root. So it's the same thing with a log. So if there is no base written in there and we have something like that, then you can assume that the base is 10 and that it's a common log. We can estimate common logarithms using our calculators and the log button. So that's actually what we're going to do just down below. And some of these I'm going to leave for you to do in your calculators because it really is just a calculator exercise. So using a calculator, you need to evaluate each logarithm to the 10,000th place. All right, so that's 4 places past the decimal. So 10,000th. I'm a liar. Oh no, that's right. 4 places past the decimal. Sorry, looked at a different example. Here we go. Punch that one into your calculator. So for me, on my simple calculator, I have to punch the number in first and do 327.1 and then hit the log button. And so it's 2.5146805 and it keeps going. So I'm going to put squiggles because it's an estimate, and it's 2.51468 and it keeps going. So then what I want you to do, so I first want you to write that for the next few examples, and then we're going to go tenths, hundredths, thousandths, 10,000ths, and then you're looking to the next door neighbor and that says for it to go up by 1, so it's going to be 2.5147 for this, and this is going to be our answer. So that's what I want you to do for the next 2 examples. Let's put it in your calculator, write down the answer here that's going to go to 5 decimal places past the decimal, or 5 places past the decimal, and then write your final answer where you've estimated it to 4 places past the decimal. So go ahead and do those 2. I'm going to give you the answers in here so you can at least check. That's what they should be. after you've figured it out and done your own rounding, and just verify that you're getting the correct answer. Okay. And then for number 2, it says using a calculator, evaluate each problem below and round your answer to the nearest hundredth if necessary. So you're going to just put this in your calculator. It's going to be 10 to the 1.5 power. So 10 to the 1.5 power for me gives me 31.622. So again, I'm going to the thousandths place because then you're going to want to round it to the hundredths place. Here's the hundredths. And again, we're going to say that's 31.62 for that one. And then for our next ones, you need to be careful with your order of operations. So order of operations on this one again, we're going to do exponents, then we're going to divide, then we're going to multiply, because remember you divide and multiply from left to right going across. So we're going to have 10 to the 16th divided by, oh my goodness, divided by 4 times 2. So now we're going to do that division. We're going to have 10 to the 4th times 2, which is going to give us 10 to the 8th. So now go ahead and we're going to do 10 to the 8th. And 10 to the 8th, it's going to give us 10 or 100, sorry, followed by 6 zeros. Because we should have a total of 8 zeros, right? Past 10 to the 8th. So 3, 6, 7, 8, which is what we have. And then I would also like you guys to rewrite that into scientific notation. So let's just do an extra practice of writing it in scientific notation and kind of refresh our brains on that. And so again, we'd move it over 3, 6, 7, 8. And so it'd be 1.0 times 10 to the 8th. All right, let's try our next one. So here we're going to do this in parentheses first. So it's going to be 10 to the negative 8 minus 2 times negative 3. And then we're going to have, let's do this multiplication. And then I'm going to think about this as being like a negative times another negative, which is going to give me a positive. So I'm going to have 10 to the negative 8 plus 6, which is going to give me 10 to the negative 2. So you might remember what 10 to the negative 2 is. You can put it in your calculator, or you can just go like this, right? Which is going to give us 1/100th. And then if we're asked to round to the hundredths, we're going to be putting that in decimal form. So 1/100th is going to be 0.1, right? 10 hundredths. So there's both of our answers for that one. So let's look at the next page. So we've got some word problems that we're going to be looking at. So let's just, the first part of this problem just gives us some context information. And I put in the reference down below. So I just pulled this from a different textbook that had some problems in it. So if you're curious about where that textbook is, it's linked down below in the footnote. Okay. It says, in chemistry, pH is a measure of the acidity or alkalinity of a solution on a scale from 0 to 14. Pure water, for example, has a pH of 7, right? It's neutral, it's right in the middle. In general, acids have pH numbers that are less than 7, and alkaline solutions have a pH value that's greater than 7. All right. The pH of a solution is defined as pH equals negative log of H3O positive, where H3O positive is the hydronium ion concentration in moles per liter. Lots of info here. All right, so then we get into part A. So part A says wetlands are classified as bogs, fens, marshes, and swamps on the basis of the pH values. A pH value between 6 and 7.5, such as that of Summerby Swamp in Michigan's Hiawatha National Forest, indicates that the wetland is a rich fen. When the pH is in between 3 and 6, so we've so far got 3 and 6, 6 and 7.5, we've got a rich fen, then it's going to be classified as a poor fen. If the pH falls to 3.0 or less, it's going to be a bog. So suppose that the hydronium ion concentration of a sample of water from a wetland is 6.3 times 10 to the negative third, how would this wetland be classified? So we are going to use this formula right here. And so we're going to plug that in. So it's going to be pH equals negative log of, and again, it gave us this, the hydronium ion concentration is right here. So we're going to fill that in of 6.3 times 10 to the negative third. And so in your calculator, again, you're going to use the E button when you're doing this. So in my very basic calculator, I'm going to do 6.3, and then my calculator has a double E button. It's right above the number 7 if you're borrowing one of my calculators. So 6.3 EE, and then I'm going to do negative 3. And then while that's in my calculator, then I'm going to hit the log button. And then whatever number comes out, I just know it's going to be negative, right? Or I'm going to, like, if my answer is negative, I make it positive. And if my answer is positive, it's going to be negative. Or you can multiply it by -1 if you want to. So what we should end up getting from this, after we take the log of that number, we should get negative 2.2006, and that keeps going, which means that we're going to have a positive 2.2006. And so how does this get classified? We'll go back up above, and it's going to be right here, 3 or less. So it's going to be a bog. This gets classified as a bog. All right, so I want you to try B because it's going to be the same type process. So go ahead and try letter B and see what you get. I will tell you that the classification at the end should be a poor fen, is what the classification should be. And I'm just going to note this, that you are doing this part on your own. So letter C does the same type thing. You're just classifying it again. So I want you to try that one out too. I'm going to note that one that you're doing this on your own. And I'm not going to give you any of the stuff for that one. So I want you to figure that one out, and then you can ask me about it in class the next time I see you. And then letter D, it says find the hydronium ion concentration. So this time we're finding the hydronium ion concentration of drinking water at the pH of 6.5. Excuse me. And then we are going to express my answer in scientific notation. So we've got this time 6.5 equals our equation of negative log, and we are doing H3O positive to do the hydronium ion, and I am solving for this. So in the next line, you're going to see me put an X in there instead. So in order to solve for that, what I want you to do first is to get the log of X all by itself. So that means I'm going to divide both sides by -1 first. So then I'm going to have negative 6.5 equals log base 10 of X. And then you need to ask yourself, okay, how do I solve this again? Well, I'm hoping that you're remembering we have a base here. You can use your rule of sevens where you're saying 10 to the negative 6.5 power is going to equal X. So 10 to the negative 6.5 power is going to be equal to X. And so go ahead and put that in your calculator and figure out what 10 to the negative 6.5 power is. And you should be getting 0. I got to count my zeros. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. You should double check me. Always make sure I'm following correct steps here. So then we're going to convert that into scientific notation. We're going to go 1, 2, 3, 4, 5, 6, 7. and it's going to be 3.16 times 10 to the negative 7th. And then I'm actually going to put my label in there too before I box my answer, but it's going to be H3O positive moles per liter is my label for that. Okay. Let's look at number 4, our decibel problem. So the loudness of sound is measured in a unit called a decibel. It's abbreviated as dB. To measure this unit, we first assign an intensity of I sub 0 to a very faint sound called the threshold sound. If a particular sound has intensity I, so this again is our particular sound. This is our threshold sound. Then the decibel level of this louder sound is given by the following equation. The table on the right gives the average decibel levels from some common sounds. So any sound over 85 decibels exceeds what hearing experts consider safe. And that means like an extended time at 85 decibels, right? Like if you're going to a concert and you're going to be in that loud environment for a while, like you could potentially experience some long-term hearing loss side effects. So that's just one of the risks, right? Or if you're constantly mowing the lawn, like that's your summer job, then I would say maybe put some, noise cancellation headphones on so that you don't hurt your hearing. So here's just some different levels just to give you a sense of where our numbers are going to come out to for the next few examples. So if music is delivered through the earphones of an iPod and it has the intensity of what's given there, 3.162 times 10 to the 9th times I sub 0. So what that means is that our sound is that many times louder than our initial sound. And I want to talk about this initial sound for a second. That's like the faintest thing that we can pick up, that we can hear. So it's not like it's 0, it's just the faintest sound that human beings can pick up in our eardrums. So now we are supposed to find the average decibel level. So we are gonna put this into our equation, and it's gonna be 10 times log of, and we're gonna put this whole thing in there because it says that the intensity of our sound is this. So it's going to be 3.162 times 10 to the 9th times I sub 0. And that's just what was given to us. And then in our formula, I sub 0 goes in the denominator. Well, that's really helpful, and that was intentional because now our I sub 0s are going to cancel out, which is the whole point of why they gave it to us in terms of that. So then we're going to have 10 times log of 3.162 times 10 to the 9th. All right, so in my calculator, again, my very basic calculator, I'm going to do 3.162 EE9. So I'm going to end up doing 3.162 EE9, and then I'm going to hit the log button. And then while that number's still in my calculator, I'm going to hit times 10. And what you should be getting is approximately 95.0 decibels. And so try that. Like, you guys need to put that in your own calculator to see what you're getting, because you want to make sure that you know how to push these buttons in your own calculator too. Don't just take my word for it. All right, natural logarithms. So far we've talked about common logs, and now we're going to talk about natural logs. So natural logs are different than common logs. So while the base of a common log, what is the base of a common log? Well, the base of a common log is, what is it? Fill it in, 10. The base of a natural log, I already told you, what is it going to be? Base of natural log is, fill it in, E, Euler's number. Although it looks like a variable, it represents a fixed irrational number, kind of like pi. And that irrational number is equal to approximately that. So the number e, like pi, is a universal constant. The letter E was chosen to honor Leonhard Euler. So you do pronounce it, I know it looks like Euler, but you pronounce it Euler. And he just did a lot of research on this number. So they ended up naming it after him. So logarithms with base E are called natural logarithms because they occur in natural situations that involve growth or decay. And honestly, it's also due to their curve. Like their curve with a, so think about this, like their base is close to 3 because it's 2.72, right? So it's a base of 3 versus a common log has a base 10. So a base 10 grows so much faster. And so that may not, I mean, honestly, common logs, you don't use them quite as often because it depends, it really just depends on the situation, right? So a common or our natural log has a base of 2.72, and so it grows, I mean, it grows fast, but it grows at a much slower rate compared to something with a common log with a base of 10. So base E logarithm of x is written as ln x. And so if you just see ln x, you just automatically know that's a natural log, and the base of that log is E. And it's often referred to as, and I keep saying it, it's often referred to as the natural log of x. We can estimate natural logarithms using our calculator and the, oh, there's a tiny little blank for that, and the ln button. So the natural log button. I want to point out too, you can also definitely use the log button, but the log, it's like if you see log and you can still write it as log base E because you can take the log of any base, right? But then in that case, we're going to have to, like if we had that log base E, you would have to do log of E. Actually, I need to switch that around. It would be log of x over log of E. So you could switch it around and do your change of base formula, writing it like that too. So that's why it's better, honestly, just use your natural log button. So your natural log has already got the built-in base of E in that button, which is perfect. Okay, so we are going to use that down here. And so it says, using a calculator, evaluate each problem below and round to the 10,000th place. So again, 4 places past the decimal. So what I want you to do is you're going to do just that. I want you to take your natural log button. So for me in my calculator, I would do 0.5841, and then I would hit the natural log button. And then what you guys, again, what I want you to do is write down 5 places past the decimal for me, which is going to be negative 0.53768, and that keeps going. So tens, hundreds, thousands, 10,000ths is here. And so it's ultimately going to be negative 0.5377 for this one. So go ahead and do that for B and C. I'm going to note that you guys are doing those on your own. And then you guys can check answers with me tomorrow or the next day I see you in class. And then for letter D, we're going to do similarly to what we did with our taking the powers of 10 to a particular exponent. We're going to do that. So here in my calculator, the E button, I have to find it. Okay, so it's above the natural log button. So you have to hit the second button and then the natural log button. So in my calculator, I would have to hit 1.5 and then I would hit the second button. and then I would hit the natural log button. Because when I hit the second button, I'm asking for it to do that other menu above the natural log button, which is e to the x above that one. So in mine, I'm going to do 1.5 second and then natural log button. And then that one gives me 4.48168, and that keeps going. So then you need to do tens, hundreds, thousands, 10,000ths. And so it's going to be approximately 4.4817. Okay, so try your next two and see what you get. So try your next two and see what you get. Be careful on this one, this last one, because the negative's on the outside of that 3. So if you're simplifying that one's, so again, doing your exponents first, it's going to be -9, not +9, because it's not like this, right? So it's going to be -9 times 2 divided by 6, multiply, divide, going from left to right. And then it's going to be -18 divided by 6, which is going to give you e to the -3rd. So just be careful on those steps. So go ahead, do those two. And then we're going to look at this number 2 example together. So it says the altitude in meters, I'm just circling my labels so I don't lose it. The altitude in meters that corresponds to an atmospheric pressure of x millibars is given by the logarithmic function defined by this. Use this function to find the altitude when atmospheric pressure is 400 millibars. And so again, we're finding the altitude in meters. So meters is going to be our label that we're going to put on at the end. And we are supposed to round to the nearest 100. So round to the nearest hundreds place. So that means we are finding f of 400. And so we're going to have 51,600 minus 7,457 times natural log of 400. So go ahead and put that in your calculator. You're going to do the 400, hit the natural log button if you have my calculator, multiply it by -7,457, and then you're going to add 51,600. So I'm just going to write some steps in, and you do your own and see what you get. All right, so rounding to the nearest 100, you should get approximately 6,900 what? Meters. Don't forget your label. All right, this is going to be a treat because you have already been doing this because I gave this to you several days ago. But it says finding logarithms of other bases. So now you know how to find base 10 and base e logarithms of any number. What if you wanted to calculate log base 7 of 36? So converting to an exponential equation, you would get 7 to what power gives me 36, right? So 7 to what power gives me 36? And you would know that it's going to be somewhere between like 1 and 2, right? Because 7 to the first is 7. 7 squared is going to be 49. So it's going to be closer to 2 than it is to 1. We don't really know for sure. So this statement right here is talking about what I was just going through. So it's going to be in between 1 and 2, closer to 2. But how close? You don't have a key for a base 7. So just like on our calculator, we've got a key for log and we've got a key for natural log. Well, we don't have a key for log of 7 because our key on our calculator for log is log base 10. So you need to use the change of base formula. To change the base of a log function to another base. So if we have a log base b of x, we can change it to any base that we want to at all. So we could say log base a of x divided by log base a of b. And that's just going to be, so let's say I choose a is equal to 10 and I say, well, I'm going to do log base 10 because that's the button I have on my calculator. Well, you can totally do that. And you can do it as log of x all over log of b. You could also change it to natural log with base e. So you could also rewrite it as natural log of x over natural log of b. Either one would be correct, and it's honestly personal preference. It doesn't matter which one you use. So log base 7 of 36, we could rewrite as this. So using a new base of 10, or we could rewrite it like this using a new base of e, so Euler's number. So now we're going to find it both ways and we're going to round to the hundredths place. So here, let's go ahead and I want you to find log of 36 and you're going to divide it by log of 7. And again, in my calculator, I have to do 36, hit the log button, then divided by 7, then hit the log button, and then equals. So again, I'm just going to write those steps out because I think you can get lost in it. So it's going to be 36 for me, then log, then divided by, then 7, then log, then the equals button. I have to hit all those buttons in my calculator. So then rounding it to the hundredths place, you should get 1.84. And then we want you to do it the other way as well. So you're going to do natural log of 36 divided by natural log of 7. So same thing, it's going to be the same exact steps, except for instead of log button, it's going to be the natural log button. So it's going to be 36 natural log divided by 7 natural log and then equals button. And you should get the same exact thing. If you didn't get the same exact thing, you need to go back and check your steps because you should get the same exact thing. All right, so problem number 1 here says evaluate log base 5 of 12 to 4 decimal places. So your choice, you can either use log base 10 or you can use natural log. So I'm just going to do common log, and it's going to be log 12 divided by log 5, and I'm going to 4 decimal places. So you guys go ahead and put that in your calculator, see what you get. And rounding to 4 places past the decimal, I'm kind of curious what 5 places past the decimal is, so I'm going to do this one. Log divided by 5 log. I got 1.543959, and it just keeps going. And I'm going to make note of that because I don't have that one written down. And then, so rounding 4 places past the decimal, that's right here. So that means this entire 39 here is going to go up by 1. And I'm going to have 1.5440 for that one. And you put the 0 on there because that's indicating to your reader that you rounded to that decimal point or that place. All right, so this one over here, I'm going to do natural log of 60 divided by natural log of 8. On your mark, get set, go. All right, so you should be getting 1.9690. And I am just going to make note of that as well because I don't have the longer decimal written down for myself. But have it for next time. Okay, so let's look at number 3. Number 3 states the amount of crude oil in millions of barrels imported into the US during the years of 1990 to 2008 could be approximated by this function given here, where x equals 1 represents 1990, x equals 2 represents 91, and so on. So estimate the crude oil imports in millions of barrels into the US in 2006. Note the actual amount was 3,685. So we're going to compare the actual to what they had predicted, just using, and that just means just using this function. So we're going to see how accurate this model or this function is that would have modeled that relationship. I'm also going to tell you that our x is going to equal 17 for year 2006. So we're going to place that in for x, and that's going to be f of 17. And we're going to have 2014 plus 384.7 log base 2 of 17. So I want you to go ahead, you're going to do your change of base for this part. And so then we're going to have 2014 plus 384.7. Let's do our change of base. I'm going to do log of 17 over log of 2. You could have chosen natural log, doesn't make one bit of difference. So then put that in your calculator. And what I am getting is 2014. So I'm going to go ahead and take log of 17, divide it by log of 2. Then I'm going to multiply that by 384.7. And I got 1,572.4469, and it just keeps going. Then I'm going to add 2014 to that, and I get 3,586.4 millions of barrels. So here again, just kind of looking back, how did that compare to what actually happened? So it looks like the model would have needed to be adjusted because this model was obviously off. It was predicting low compared to what we actually used. All right. So for our next portion, kind of like switch gears a little bit from what we were doing, and we're going to work on graphing exponential and logarithmic functions of base 10 and base e. And what we're actually going to do, you're going to see me graphing them using base e, because I have a feeling you would probably do just fine doing graphs of base 10. So that's what we're going to look at for the last portion of this video. So it's going to be this page and then the next page, and we're going to do some graphing, and then that'll be the end of this topic. All right, so graphing functions with base 10 or base e is no different than graphing other exponential and logarithmic functions. So it's, the process isn't going to change, we just have a different base. So we're still going to create a table of values. We're going to plot the points. We're going to connect the points with a smooth curve. Also, for our table of values, we are always going to use -2, -1, 0, 1, and 2. That's just going to be consistent for all of our exponential and logarithmic functions. So again, because we've got 3 functions here, what I would like for you to do is get out some, if you have different colored pens or pencils, like different colored, like types of colored pencils, you can use that. If you don't, you can just say, well, this is going to be my solid line, this will be my dashed line, and maybe this is your dotted line, or do something else, however you'd like. But I would label them out, or do something a little different, because otherwise it's just going to look like a big mess on your paper. All right, so for our first function, I'm going to do x and we're going to do that same thing where we just do e to the x, and then we're going to have a y, and then we're going to have an ordered pair. So this is the other thing I'm going to tell you. It might be a little bit easier for you. Instead of doing an e, you are allowed to use 2.72 instead of e. So on mine, it's a little bit tricky to get to the e button. And so if you would rather, you are welcome instead right here to do 2.72 to the x. So you're plugging in 2.72 instead, your choice. All right, so here we're gonna have -2, and then we're gonna have -1, and then 0, and then 1, and then 2. All right, so we've got e to the -2, which again, you can just put that in your calculator. You can do e to the -2, or you can do 2.72 to the -2 power. And what you should be getting out is 0.14 for that. And then we're going to get -2, 0.14 for that ordered pair. Then we're going to do e to the -1. Again, you could also just put 2.72 to the -1. I don't care. Pick whichever one's easier. Then we're going to get 0.37, which is going to be -1, 0.37. Then we're going to have e to the 0, which is going to give us 1. So we're going to graph the 0.01. Then we have e to the 1, which is going to give us 2.72, which is going to be 1 and 2.72. Then we're going to have e squared, which is going to give us 7.39. And then we're going to have 2, 7.39 for that. So now let's graph those. So again, these are going to be a little bit harder to graph. And then the next ones, the one I'm going to give you next is going to come on the inside of this point, and the other one's going to go on the outside. So we don't have to sneak in 2 like we normally do. So this one, we're going to have -2 up 0.14, which is going to be kind of hard to graph in there. And then I'm going to do -1 and 0.37. So just going to stick it in there too. And then 0, 1. And then we've got 1, almost 3, right? And then we've got 2, about 7.5. 5, 6, 7. So about like that. All right. So for that one, again, I'm just going to label it. That's going to be e to the x. So the next one, I'm going to be consistent and make this one blue here. So then we've got x, e to the 2x, and then y, and then our ordered pair. So it's going to be -2, -1, 0, 1, and 2. And here we're going to have e to the 2 times -2. So it's going to be e to the -4. So again, you could put 2.72 if you'd rather. So you can do 2.72 to the -4 if you'd rather. And we're going to get 0.02. So we're going to have -2, 0.02. Then we're going to have e to the 2 times -1, which is going to give us e to the -2, which is going to give us 0.14, because we did that one actually up above, right there. And then we're going to get -1, 0.14. Then here we're going to get e to the 2 times 0, which is going to give us e to the 0, which is going to give us 1. So it's going to be at 0, 1. Then here we're going to get e to the 2 times 1, which is e squared, which we already did right here. So it's going to be 7.39. It's going to be 1 comma 7.39. And then here we're going to get e to the 2 times 2, which is going to be e to the 4th, which is going to end up giving us 54.60. So this one really increases a lot faster. And then we've got 2 comma 54.60 for that one. All right, so graphing -2. So this one's going to be underneath this dot. And then -1 is going to be, so we've got 0.14 in here. It still is going to cross at 0, 1. And then we've got 1 at 7.36. And then 2 is going to be way up here at 50. I mean, that's kind of ridiculous. It's going to be like way up here. I don't know, just do your best. I don't even know if that's lined up vertically. And then my other points already moved on me. So these points, the blue points, had been below. So it's going to be like this, and then it crosses, they intersect at 0, 1, and then it's going to drastically increase. Yeah, and I totally missed my point, but you get it. You get the idea. And then this one's going to be 2, like 54, what was it? 54.6, yeah, 54.6 there. And my line keeps moving, so I hope you saw it before it keeps moving. So the blue is underneath that red line, and then it finally crosses at 0, 1. But I'm sure next time I rotate around, see, it just moved again. Sweet. All right. Then our next one, we've got x, and then we've got e to the 0.5x, and then y, and then our ordered pair. So again, we're going to have -2, -1, 0, 1, and 2. And so we're just going to fill it in. E to the 0.5 times -2. So half of -2 is going to give us -1, right? So e to the -1. It's going to give us 0.37. So -2, 0.37. And then we've got e to the 0.5 times -1, which is going to give us e to the -0.5, so the -half. And then we should be getting 0.61 for that. So it's going to be -1, comma 0.61. And then e to the 0.5 times 0 is going to give us e to the 0, which is 1. And it's going to give us 0, 1. And then e to the 0.5 times 1 is going to give us e to the 0.5, which is going to give us 1.65. So we have 1 comma 1.65. And then e squared, or not e squared, but e to the 0.5 times 2 is going to give us e to the first, which is only going to give us 2.72. And then we've got 2 comma 2.72. And I'm just going to give you one more ordered pair so we can just graph it as well. And it's going to be 3 comma 4.49. So this one does not grow nearly as fast. So my lines are all over the place because the technology here keeps moving my line everywhere. Anyway, all right, so -2 to the 0.37 should be above my other 2 points based on where I had originally put them. And then -1, so same story. It should be above my other 2 points compared to where I'd put them originally. Again, they've moved, and I apologize about that for technology getting in the way here. And then we've got 1 comma 1.65. So 1 1.65, and then we've got 2, comma 2.72, so almost 3. And then we've got 3, comma 4.49. Right? Yeah, sorry, mine's way at the bottom. 3, comma 4.49. All right, so then that one would be above the other two crosses and then comes on the outside like that. Okay, so observations to note. All 3 graphs intersect still at 0, 1. And base E remains the same. Well, why is that? Why did I even point that out? Because I'm hoping that you notice that this time we've got like a stretch going on. So our graph is like stretching and getting wider and then kind of compressing because we've got, let me show you. Like here we've got e to the x and e to the 2x, and then e to the 0.5x. And so we're doing something different here with our x's, right? And so we're doing what's called a shift on our graph on this one. And so we're doing like a transformation, whereas the other problems, if you remember on exponential, we did something like this. We did 2 to the x, 3 to the x, 4 to the x, and each of those have different bases, but they're all raised to the x, right? Like we did nothing to our exponents. They all were just an x. Well, here we went from x to 2x to half an x. And so that's the part that's changing. So that's why I put that in here, that our base E remains the same rather than here when we changed our base. So that's why. So as exponent, so this time we're going to talk about how as the exponent changes versus when the base changes, because the base didn't change. So as exponent increases, and for x values greater than 0, the curve gets steeper and closer to the y-axis. The curve gets steeper and closer to y-axis. As exponent increases and for x values less than 0, the curve gets closer to the x-axis. Okay, so how would our graph look the same or different if the base was 10 instead of E? So they'd have similar shapes, right? The shapes of the graphs are going to still be the same, like they're going to follow the same trend, but it's going to increase at a much, much faster rate if at a greater base, right? Because the base would be 10 instead of E. So that's what we're going to put in here. Similar shapes. But that should be they, but they would increase, decrease at a much faster rate. All right. So now we're going to look at the natural logs and graphing them. So we've got 3 again, and we've got our natural logs. What was our first step 100% of the time when we're graphing logarithmic curves. Hoping you remember this. So our first step always is to convert them into exponential form. So I'm going to convert these. So we've got natural log of x equals y, or f of x, but I'm going to put that as y right now. And we're going to do e to the y equals x. So it's going to be e to the y equals x. Then for this next one, we've got a little bit more work to do, so be careful on this one. We've got e to the y equals 4x, and we still have to solve for x. So we're going to divide it by 4, divide it by 4. So we've got e to the y divided by 4 equals x. If you want to, I think it's a little bit easier to put in your calculator. So I want you to think about this, how this is like 1/4 times e to the y, which is going to be 0.25 times e to the y. So I either think you put it in your calculator like this, or you put it in your calculator like that. Your choice for how you'd like to work with it in your table of values. Then for our last one, we're going to have, again, we've got natural log of 0.5x equals y. So it's going to be e to the y equals 0.5x. So I'm going to write right over my graph, and then I'm going to erase it. So we've got e to the y equals 0.5x. I'm going to divide by 0.5. And so again, keep in mind what we're doing here. So like if you actually have e to the y over 1/2, that's like you take what's in the numerator, you keep, change, flip. So you're gonna, when you divide by a fraction, you end up multiplying by the reciprocal of that second fraction. So it's gonna be times 2 over 1. And so we're gonna get 2e to the y for that one. So this is gonna be 2e to the y for that one. Okay, so I'm gonna write up my 3 grids, or my 3 tables, and I've got x, and then I've got e to the y, and then I've got y, and then I've got my ordered pair. So then here I've got -2, -1, 0, 1, and 2, and you're going to plug it into your values. So we've got e to the -2, e to the -1, e to the 0, e to the 1, e to the 2. And again, you could do 2.72 instead of using e. Totally your choice. So I'm just going to fill in my values here: 0.14, 0.37, 1, 2.72, 7.39. And then writing in my ordered pairs: 0.14 comma -2, 0.37 comma -1, 1, 0, 2.72 comma 1, and 7.39 comma 2. You know what? I might try graphing at the end and see if my graphs move less on me that way. All right, next one, I'm gonna do x. And I don't remember what my other one, is this 0.25 one. All right, so we've got 0.25 e to the y, or you could do this one, e to the y divided by 4, whichever one you want to do. And then it's going to be my y values and then my ordered pair. So then I've got -2, -1, 0, and 1 and 2. So 0.25 times e to the -2, 0.25 times e to the -1, 0.25 times e to the 0, 0.25 times e to the 1, 0.25 times e to the second power. So again, I encourage you to do this on your own and putting it in your own calculator to make sure that you're getting the same answers. I'm just going to write in what I got, but you should verify that you are getting the same information. So I got 0.03, 0.09, 0.25. This one's going to be exceptionally maybe difficult to graph. 0.68 and then 1.85. And then I'm just going to give you a couple more ordered pairs for this one because this one, as you can tell, it's hardly growing. It's not growing at a very fast rate. So then the next one I'm going to give you is 5.02. And that's going to be e to the third. And then I did one more because this one grew so slowly, 13.6. So that's going to be 0.25 times e to the fourth. And then the other value is going to be 4. So I'm going to fill those in as my ordered pairs. So it's going to be 0.03 comma negative 2, 0.09 comma negative 1, 0.25 comma 0, 0.68 comma 1, 1.85 comma 2, 5.02 comma 3, and 13.6 comma 4. So you've got those, and then I'll graph those shortly too after I do my last table. So what's the color I haven't used? Blue. Here we come, blue. X, gonna fill in my function. This time my function is 2e to the y, and it's gonna be my y and then my ordered pair. We're gonna have negative 2, negative 1, 0, 1, and 2. If I am you, you should pause the video right here. Pause it, see if you can fill in your table without any help, and then check your answers at the end and see how you do on this one. All right, so here I've got 2 times e to the negative 2, 2 times e to the negative 1, 2 times e to the 0, 2 times e to the 1, 2 times e to the second power. Then my answer here is going to be 0.27, 0.74, then I get 2, then I get 5.44, and then I get 14.78. And so then we're getting 0.27 comma negative 2, 0.74 comma negative 1. We're getting 2, 0 for here, 5.44 comma 1, and then 14.78 comma 2 for that one. All right. I'm gonna graph. All right, so purple first for my first one. It looks like 0.14 negative 2. So 0.14 negative 2. And then 0.37 negative 1. And then I've got 1, 0. And then 2.72 comma 1. And then 7.39 comma 2. All right, so that's the first one of just our generic curve of e to the y, or natural log of x, is what that one looks like. My next one is red. And so this time I've got 0.03 negative 2. So this one's going to be even skinnier in here. So 0.03 negative 2. And then 0.09 negative 1. And then 0.250. So check that out. It's the first one that hasn't hit 1, 0 so far. 0.681. So 0.681. And then 1.852. And then 5.3. And then I did 13, 4. So that's going to be what? 5, 6, 7, 8, 10. I don't know. We're going to guess like about right here. All right. Last one. Oh, I'm about to sneeze. Okay. 0.27 negative 2. So 0.27 is going to be on the out, like to the right of these other two that I've already graphed. So 0.27 negative 2. And again, I know that's not super accurate. We should be further to the left, but we're doing the best we can here. 0.74 negative 1. 2, 0. So check that out. It didn't hit 1, 0 or 1, 0 either. So we got 2, 0. Then we got 5.4. So I'm going to say like almost 5.5, 1. So 5.4, 1. And then about 15, 2. So 15 is going to be way over here, 2. So what in the world? These graphs look quite a bit different compared to our other log graphs that we graphed like a few days ago, where we had log base 2 of x, and then we had log base 3 of x, and log base 4 of x. And then we also did something where it was like log base 1/2 of x and log base 1/3 of x. So again, what I'm hoping you're seeing is that every single time our bases are the same, right? So our bases for these are going to be the same because the base is always base E. And so like this one was natural log of 4x. And then the blue one was natural log of 0.5x is this one. And so looking at how those different graphs change based on how our coefficient in front of the x is changing, right? So observations to note. 1, none of the graphs intersected at a particular point on this one. So, you know, like all the other graphs, they've always intersected at like 0, 1 or 1, 0. That's not true on this one. Other things I'm noticing is that they are nesting inside each other. So they look almost like the exact same curve, but they're growing at a different rate, right? So we're gonna fill in some of those things. And then the base E remains the same, like our base didn't change at all on those. All right. So only one graph, and that would be natural log of x, hit 1, 0. And no graph intersected with another graph. They just, and actually I'll put that in a new bullet. Same trend line. Nested within one another. Just growing at different rates. Base E on all graphs. So again, that is just to contrast with the other logarithmic curves that we graphed where the base was different. What else? All right, I'm gonna fit in 2 more things and I might have to use some space down below. But one thing I'm gonna add in is as the factor increases. And for y values greater than 0, the curve gets closer to the x-axis. And then I'm going to do one more down here. As factor increases, and for y values less than 0, the curve gets further that R does not look like an R, gets further from the y-axis. So this one actually goes up here. All right, to answer this last question. Also, how would your graph look the same or different if the base was 10 instead of E? This is going to come down here. So again, similar shapes, right? So similar shapes, it's just going to be increasing or decreasing that much faster because the base is going to be 10 instead of E. So similar shapes. But they would be increasing or decreasing at a much faster rate. So like they're either pulling towards the x-axis or pulling the other way towards the y-axis at a much faster rate and kind of growing along each of those axes at a much faster rate depending on what the function looked like and then having the base of 10. Okay, that is it for this topic. Thanks for hanging in there. It was a little bit longer of a topic and I appreciate you guys just following along. And if you have questions, please just ask me in class. Thanks, bye.